we're going to continue today talking about convergence of random variables, and we're going to look at some examples, and then we're going to look at some other applications, and hopefully we're going to end up talking about the central limit theorem, which is one of the kind of most important theorems in maybe all of mathematics, and certainly one of the most important in probability and statistics. And we're going to talk about what it is, which can now be kind of properly introduced through convergence topics, and then we're going to do a short little proof of the central limit theorem. And so I think that would be a nice way to kind of close out the course, going all the way from knowing nothing about probability to proving the central limit theorem. So we're going to start with an example, just to review. So last time we had talked about convergence almost surely, which was basically said that that the random variables converge pointwise for a very large set of the sample space. And we talked about convergence and probability, which said that the probability that our sequence elements are far from the limit kind of goes to zero as we go out in our sequence. And then we talked about convergence and distribution at the end of the last lecture, and that convergence and distribution was just that the CDFs converge in a pointwise fashion. So let's start and look at an example. In our example, we're going to have a sequence x1, x2, x3, etc. And all of these are going to be IID uniform 0, 1. So they all come from a uniform 0, 1 distribution, and they're all going to be independent. And we're going to define from these y sub n to be the maximum of the first n of them. I goes 1 to n, the maximum of these x sub I. So y sub 1 is just x1, y2 is the maximum of x1 and x2, y3 is the maximum of x1, x2, and x3, and so forth. Now, if you think about this problem, or this random variable y and what it is, if I have my unit interval here from 0 to 1, then if I collect my x's over time, maybe my first x falls here, second one here, third one here, fourth one here, we're going to get, since these are uniform, we're going to get a uniform spread in the limit here of y's of points in our unit interval, and we expect that as we do this over time, the maximum one of these should eventually start getting really close to 1. So our intuition is that these y sub n's should somehow approximately be 1 for large n. And the way we can formalize that is with the convergence. And so we're going to look at how to show. First, we're going to show that these y sub n's converge in probability to 1. And so the maximum converges in probability to 1. What I mean when I say converges to 1, so before we've talked about how random variable some x sub n's converge, say, in probability to another random variable x. So what does it mean to talk about some x sub n's or some y sub n's converging in probability to a number? Well, a number we can think of as a degenerate kind of random variable. It's going to be degenerate random variable. You could call it y, where the probability that y is equal to 1 is 1. So with probability 1, it takes on y. Its PMF would look like at 1, it would have a stick of height 1. So this would be its PMF. Let's say f sub little y. So we can talk about converging to a degenerate distribution, which is kind of how we can make sense of the notion of random variables converging to a number. So let's see if we can show that Yn converges in probability to 1. And this is going to tie together the last lecture when we talked about inequalities, because showing that this thing converges in probability to 1, we're going to do through the use of some inequalities. So recall that our definition is that the y sub n's are going to converge in probability to y. This means that if I look at the probability of that yn minus y is bigger than any epsilon. So I pick an epsilon and I say, what's the probability y sub n is more than epsilon away from y? As I increase n in the limit as n goes to infinity, this is going to go to 0. So in the limit, the probability that y sub n is far, that is more than epsilon from y, is 0. And we can play that game for all possible epsilon. We can say that yn converges in probability to y. So pick however the distance, however far away you want yn to be from y. As for a small distance epsilon, there's always going to be, we're always going to have that the probability that yn is more than epsilon away from y goes to 0. So our central item that we want to use when proving convergence probability is this probability statement. The probability that yn minus y is bigger than or equal to epsilon. You could alternatively show that this probability that's less than epsilon goes to 1. But this is typically the easier way. So we want to look at the probability yn. In this case, y is just 1. So yn minus 1 is bigger than or equal to epsilon. And we could also, since we can flip around the order in the absolute value, we could say this is 1 minus yn bigger than or equal to epsilon. And because the x sub n, all these x sub n's are bigger than or equal to 0, y sub n's will be bigger than or equal to 0. And because the x sub n's are less than 1, the maximum of the x sub n's will also be less than 1. And so 1 minus y sub n is always going to be a positive quantity. So we can actually forget about our absolute value bars. This is just 1 minus yn bigger than or equal to epsilon. And we can rearrange this as the probability. We can move y to the other side. We can flip things around. This is the probability that yn is less than or equal to 1 minus epsilon. So recall that y sub n is the maximum of these x sub n. So if the maximum is less than or equal to 1 minus epsilon, then we know that this means each of the x sub n's must be less than or equal to 1 minus epsilon. So x sub 1 has to be less than or equal to 1 minus epsilon, x sub 2, and all the way up to x sub n must be less than or equal to 1 minus epsilon. And because they're independent, we can just calculate this as a product. So it's the product that each of these x sub i's are less than or equal to 1 minus epsilon. And since these x sub I are uniform 0, 1, then the probability that any of them, x sub I, is less than or equal to some, well, let's just say some value little x, is just little x. This is the CDF. This is the CDF of a uniform 0, 1. And so continuing our chain here, this is the product, and the probability any of these x sub I is less than or equal to 1 minus epsilon is just 1 minus epsilon. So we get just the product of 1 minus epsilon n times, so it's 1 minus epsilon to the n. And so what we're calculating here, if we recall from up here, this is the probability y sub n minus 1 greater than or equal to epsilon. And what we've shown here is that that is equal to 1 minus epsilon to the n. And there's technically a caveat. This is for epsilon less than or equal to 1. If epsilon is greater than 1, it's trivial. The probability yn is more than 1 away from epsilon is 0, always, because of the bounds of our random variables. And so you can think about that case, but it's a pretty easy case. Turns out it was always 0. In the case of epsilon less than 1, we get the probability that y sub n is more than epsilon away from 1, is 1 minus epsilon to the n. And so we get that the probability that yn minus 1 greater than or equal to epsilon, as we increase n, as n goes to infinity, that converges to 0. And so by definition of convergence in probability, y sub n converges in probability to 1. Okay, so we've shown the result. So this shows and backs up our intuition, which is that the maximum of these uniforms should get closer and closer and closer to 1. And in a very formal sense now, we can say that. Say in probability, it converges to 1. So we can also ask, and indeed we will show, that y sub n converges in distribution to 1. So if you recall that convergence and distribution means that if I look at the CDF of each of these y sub n's, this will converge pointwise as a function to the CDF of y. Well, what was y? Y was our degenerate random variable, and the PMF of y, so the PMF of y was just a stick at 1 of height 1. So that's the PMF. And so the CDF of our limit y in this case is going to be what? Well, if we're less than 1, it's just going to be 0, and then it's going to jump up to 1 at 1. And so it's just a perfect step function at 1. So it's a step function at 1. Why do we need this? Well, we're going to show convergence and distribution, we have to show that the CDF of the y sub n's converges to the CDF of y, and we need to know what the CDF of the y looks like. Turns out it's really simple. It's just a step function, steps from 0 to 1 at 1. Okay, so now let's show that this result here, which is that y sub n converges in distribution to 1. So what do we need? We need the CDF of the y sub n's. So f y sub n of little y is defined, of course, to be the probability that y sub n is less than or equal to little y. And kind of as we saw above, if y sub n is the maximum, this is just going to be the probability. If the probability of the maximum is less than or equal to little y, it's just the probability that all of them are less than or equal to little y. And, of course, this is the product. Because the x of I are independent, this is just the product of the probability that each of these x of I is less than or equal to little y. And again, as we saw last time, this is basically just going to be y to the n. We have to be a little bit careful because it's y to the n as long as y is between 0 and 1. If y is less than 0, the probability any of these x of I is less than that is 0. So it's 0 if little y is less than 0, and if little y is bigger than 1, each of these is 1, and so it's just 1 if y is bigger than 1. So this is our CDF, just pulling this down here, this is our CDF of y sub n, of f of CDF of y sub n, right? So that's CDF of y sub n in the green box here. On the right, we have the CDF of y. So this is CDF, let's say, of capital Y, which is our limiting, our proposed limit. And so what the argument you have to make now is that as n goes to infinity, f sub y n of little y goes to what? Well, if little y is less than 0 or little y is greater than 1, that doesn't change. But as n goes to infinity, if y is between 0 and 1, this thing is the y sub n is going to go to 0. So I would say because y sub n is going to go to 0 as n goes to infinity, and that is true for any y in this interval, right? I take a number between 0 to 1 and raise it to powers, it gets smaller and smaller and smaller and smaller. And so this is for any of those, and this is exactly, so we can simplify our cases here. It's either 0 or 1, it's 0 if y is, let's say, less than 1, and 1 if y is bigger than or equal to 1. The endpoints, I guess, we have to be a little bit careful, but we can fudge that a little bit. So, and this is equal to the CDF. This is the set function, which is the CDF of our degenerate random variable. And so we have that in the limit, so we should really write as n goes to infinity, you get the CDF of the y sub n gives you the CDF of y. And by definition of what it means to converge in distribution, we can say the y sub n converge in distribution to the y. And in this case, y was 1, was our degenerate, so we just write 1. A little bit of abuse notation, but not too bad. So we saw, in this case, that it converged in probability to 1, and we can, so it converged in probability to 1, and it also converged in distribution to 1. So there's a theorem that says this always has to happen, which is that convergence in probability implies convergence in distribution. So if x sub n, kind of formally write this out, if it converges in probability to x, then x sub n will converge in distribution to x also. And this is an example of the above, this is the generalization of the above fact we saw, which is a conversion probability 1 and a conversion distribution to 1. And there's a theorem, which we won't prove, but that says that always has to happen. So we now have a chain of our 3 modes of convergence. Almost sure convergence implies convergence, let's say IP in probability, and that implies convergence in distribution. So almost sure in probability and in distribution. Say in distribution. And so that's the chain. So the strongest mode of convergence is almost sure. Slightly weaker is convergence of probability, and then even weaker still is convergence in distribution. Now we had an example where a of random variable converged in probability, but not almost surely. So we know part of this converse doesn't work, and the question is, if it converges in distribution, does it always converge in probability? Well, the answer is no. Otherwise, we wouldn't have different names for these. So the converse implications generally are not true. And we'll talk about some special cases where they are, but in general, you cannot go the other way for either of these. Okay. So let's look again at our example. That's kind of a weak example of convergence and distribution because it was a degenerate distribution. So let's revisit our example. And instead, let's define z sub n to be n times 1 minus y sub n. So we're defining a new sequence of random variables based on those old y sub n, and recall that y sub n was our maximum of the first n of the x's, and the x's were IID uniform 0, 1. So let's see if we can get some kind of, let's see if we can figure out what does this z now converge in distribution to. We said that yn converges distribution to 1. So if you just plugged in 1, it would seem like z sub n should converge in distribution to 0. So let's take a look. What we need so let's just write a note for ourselves and say distributional limit. What we need for ourselves is a to look at the distributional limit is we need to find the PDF the CDF of z sub n. So we're going to f of z sub n of little z, which is the probability z sub n less than or equal to little z. And of course we define z sub n as the probability as n times 1 minus y sub n. So we can substitute that in. And now we're going to do some algebra. So this is the probability that y sub n is greater than or equal to 1 minus z over n. And that's just a little bit of algebra. Divide through by n, and move y to the other side, and then subtract z over n. And we can rewrite this as 1 minus the probability y sub n less than or equal to 1 minus z over n. Why do we want to do that? Well, y sub n is the maximum, and so as we saw before, this is 1 minus the product that of the probability that each of these x sub I are less than or equal to 1 minus or whatever value. And we can calculate what that value is, right? These x sub I are uniform, so recall that that my x sub I are uniform 0, 1, they're IID, uniform 0, 1, and so if I can look at the CDF of my x sub I, which is effectively what we want to calculate here. This is 1 minus, and then we're going to get a couple different cases. If z over n, let's write this a little better, z over n is bigger than or equal to 1, we're going to get 1. that right? Let's be real careful here. I think it's if we're going to get 0 in that case, right? Let's back up. If z over n is bigger than 1, then 1 minus z over n is less than 0, so we should get 0. If z over n is less than or equal to 0, we should get 1. And the other cases, where z over n between 0 and 1, we'll just get 1 minus z over n. And this is just comes from the fact that we're plugging into the CDF of an IID uniform 0, 1. And so we can write this in kind of a less crazy way here. Let's combine these. It's 1 minus z over n, which should give me z over n. And then we get 1 minus 0, 1 minus 1 is 0. So this is, the first case is 0 less than z over n less than 1. This is z over n bigger than or equal to 1. And this is z over n less than or equal to 0. Okay. And so what we've calculated here now is we've calculated the CDF for z sub n. So we define z sub n in this kind of funky way up here, and all this was just to get the CDF of z sub n. So this is f zn of little z is what we've derived at this point. And we got to be careful. Let's back up here. Not quite right? This should be to the n, so it's not going to... Let's be real careful. This is 1 minus z over n to the n. Sorry, right? So when we went from this step here, this was, we had the probability of any of the little x sub I being less than 1 minus z over n was 1 minus z over n. But we had n of them, so we raised it to the nth power. Okay, so this... Just fix that, bring that to the power of n. We can't do as much cancellation, but this is what our CDF is. So what's the limit? What is the limit of our CDF? Whatever the limit of that is, we're effectively going to converge in distribution to what that is if it has a kind of reasonable limit. And as n goes to, as n gets larger and larger, we're never going to run to the case where z over n is always bigger than or equal to 1. Otherwise, z would have to be bigger than every positive integer, so we don't really have to worry about this case as much. And so we're kind of going to get two cases here. F Zn of z is going to converge. Well, it's going to always be 0 if z is less than or equal to 0. Okay. If z sub n, if z over n is between 0 and 1, which means, which is kind of the interesting case here, then this thing is going to go to 1 minus e to the negative z. So you can see that, if you recall what the definition of e, so e is the limit as n goes to infinity of 1 plus 1 over n, the n, and so e to the c is the limit of 1 plus c over n to the n. And in this case, our c is negative z. So the limit of, as n goes to infinity, of 1 minus z over n to the n is equal to e to the negative z. So this is what we get for our CDF. It's 0 if z is less than or equal to 0, and it is going to be 1 minus e to the negative z if z is positive. And we can recognize this as the CDF of an exponential distribution with a rate parameter of 1. And so what this means is that the z sub n, which is 1 minus, it's n times 1 minus the maximum, converges in distribution, because we've shown the CDFs converge, to let me write it this way, an exponential 1. So that's a kind of more substantial example of convergence and distribution. It's not a degenerate distribution, it's a real distribution. It's an exponential 1 distribution. So we've now talked about 3 modes of convergence. We've talked about convergence almost surely, convergence and probability, and convergence distribution. We looked at examples, and we kind of looked at how they're related. And we're going to talk a little bit more about some of the properties of convergence, some of the kind of useful algebraic properties. The first theorem we're going to state is that it's a partial converse. We know that convergence almost surely implies convergence in probability, implies convergence in distribution. And so we have our theorem is a partial converse, and the theorems that follow kind of rely on this. The partial converse is that if we have a set of random variables x sub n, and they converge in probability to and they converge in distribution to some constant, then they're also going to converge in probability to that constant, where c is a constant, i.e. a degenerate distribution. So our theorem normally says that almost sure implies improbability, implies distribution, but you can't go the other way. If a random variable converges in distribution, we don't necessarily know it converges in probability. The partial converse says that if we know it converges in distribution to a degenerate constant, to just a degenerate distribution, to a constant, then actually we can say that it implies that it converges in probability to that constant also. So that's just a very useful theorem. It's a partial converse for our chain of implication that we built up. There are also some other algebraic properties that we can write down. And the other algebraic properties that we can write down are, so we could say if x sub n converges to x, and we have some other sequence y sub n that converges to some y. And they're going to be very vague, purposefully, about what kind of convergence. In this case, we know that a x sub n plus b y sub n converges to ax plus by. So that addition and multiplication, linear combinations, are preserved, and x sub n times y sub n converges to x times y. And this is true for either almost sure convergence and convergence in probability. So if x of n converges almost surely to x and y sub n converges almost surely to y, this is true. Or if x of n converges in probability that x and y n converges in probability to y, is also true. It doesn't work for, is generally not true for convergence. Not generally true for convergence and distribution. So unfortunately, we don't get these nice algebraic properties for convergence and distribution, but we do for convergence almost surely and convergence and probability. Some other useful theorems. There's a theorem called Schlotzsky's theorem. And Schlotzsky's theorem is kind of the algebraic properties for convergence and distribution. So algebraic properties for convergence in distribution. It's a partial theorem. We have the full theorem, but it's kind of a partial theorem. And it says that if x of n converges in distribution to x and y sub n converges in probability to a constant, then we get some reasonably nice algebraic properties. Xn plus yn converges in distribution to x plus c. Xn plus yn converges in distribution to x times c, and xn over yn converges in distribution to x over c. And what I mean is that you're just scaling, you're either adding constantly random variable or scaling it by c or 1 over c. So for convergence and distribution and convergence, almost surely we get the algebraic properties kind of for free. For convergence and distribution, can't quite do the same things. It doesn't necessarily work that way. But if we have another sequence that converges in probability to a constant, then we can do algebra with that other sequence, and things work out nicely. Additionally, we have a theorem about transformations of limits and of sequences. And while you might be traumatized by the transformation theorems we've had so far, this one is actually very nice. It's called the continuous mapping theorem. And the continuous mapping theorem says that if G is a continuous function, so some real valued function, r to r, and it's continuous, and xn converges to x, let's say, by any mode, doesn't matter if it's almost surely, it's in probability, it's in distribution, then G of xn converges to G of x. So we can just apply G to both sides of the limit, and everything works out hunky-dory. This may seem like kind of an amazing theorem, because you get everything for free. And so we can say this is true for any type of convergence. But if you take an analysis class, so kind of as an aside, in an analysis class, the definition of a continuous function G is that if we have a convergent sequence, xn converging to some x, then G of xn converges G of x. So we should probably say for all. So in an analysis class, the way you define continuity correctly is that a function g is continuous if it preserves limits of any convergent sequence. So if you pick a sequence, xn goes to x, g of xn must go to g of x. If it does that for any convergent sequence, then the function is continuous. And so in that light, it's not maybe too surprising that given our probabilistic definitions of convergence, it also preserves limits of continuous functions. Nonetheless, a super nice theorem. Okay. So, for the last part of this lecture, I want to talk about means. And we're going to close out with the central limit theorem. The central limit theorem talks about means. And so our intuition is that if I have some x sub I, following, let's say x sub I and their IID from some PDF or some distribution, little f. And if the expected value of any of these is some value mu, the mean, then my intuition is that if I look at what we're going to call x bar sub n, which is the arithmetic average of these x sub i's, this thing should be a good estimator of mu. Now, if you want to really dive into that question, you should take 452. But the intuition is that x bar, the sample mean, is a good estimator of the mean, mu. And so if I have some data from some distribution that I take x bar, that should give me something that somehow, when I have a large enough sample size, should give me something that's a reasonably close to mu. So that is xn bar approximately mu for large n. Now that saying x bar at xm bar is approximately mu is very hand-wavy, but we've now built up a whole machinery of convergence of random variables, and so we can precisely talk about that. And we've talked about 3 different modes of convergence: almost sure, improbability, and in distribution. And so there are going to be 3 different ways of talking about how xn bar approximately is mu when n is large. So the first 2 ways are called the laws of large numbers. So let's start off with the first one, which is called the weak law of large numbers, often abbreviated WLLN, weak law of large numbers. And the weak law of large numbers says that if we have some x sub I that are uncorrelated and 1, they all have the same mean. Expected value of x sub I is mu, and 2, the variance of each of these x sub I is finite. So they somehow have a finite variance, and they all share the same mean. In this case, the weak law of large numbers says xn bar, which is a sequence of random variables. You can collect more data, and you have a larger and larger n, you have a sequence of random variables. This thing converges in probability to mu. And so it's called weak because because it's convergence in probability. There'll be a strong law for convergence almost surely. But it says that if we collect enough, then in probability, this sample mean will converge to mu. So we're not going to prove the whole most general case here. Let's do a proof of a simpler case where all of them are IID. So let's assume x sub I are IID from some distribution f. We don't really know what the distribution is. All we know is that the expected value of each of these things are mu, and we're going to assume they not only have the same mean, that they all have the same variance. So there's some distribution with a mean mu and a variance sigma squared, and they're all IID from that distribution. Then we're going to make a couple observations. One, if I look at the expected value, let's try this, expected value of Xn bar. This is the expected value of 1 over n of the sum of the x sub i's. And I know that with expected value, I can push it through constants, and I can push it through sums. So this is 1 over n. Sum goes 1 to n, expected value of x sub I. And so this is 1 over n times sum. Each of these expectations is mu, so I get 1 over n times mu is mu. So the expected value of x bar is mu, is our mean. Well, that's good. And expectation x bar should at least be our mean. We can also notice that if we look at the variance of Xn bar, this is the variance of 1 over n, I goes 1 to n, x sub I. Now, because these x sub I are independent, we can pull out our n. 1 over n is an n squared always, but because they're independent, I can push my variance through, and I get, I can write this as the sum of the variances, and because I couldn't do that unless they're independent, but because they're independent, I can push the variance through the sum, and all of these have the same variance, so I sigma squared, so I just get n sigma squareds, and so we get sigma squared over n. So the expectation of x bar is mu, and the variance is the variance of them individually divided by n. Now we're going to apply Chebyshev's, because Chebyshev says that the probability that absolute value of some random variable x minus its mean over sigma, probability of that is bigger than or equal to. So we had a version that said if it was bigger than or equal to epsilon, that was less than or equal to sigma squared over k. No, sigma squared over epsilon squared, right? There we go. That's the right form. Okay, there we go. So if you look back in the notes about Chebyshev, we said that the probability that x minus mu over sigma greater than epsilon, we could write as saying that is bounded above by sigma squared over epsilon. So now we're going to apply this to x bar. So let's say apply to x bar sub n. And remember that the expected value of x bar n is mu, the variance of x bar n sigma squared over n. And we can rewrite this, let's just rewrite this in a more general way. This says that x minus its expectation any random variable minus its expectation divided through by the square root of its variance and was the probability that's bigger than or equal to epsilon is less than or equal to variance over epsilon squared. And so now we can apply this Xn bar. We know what its expectation is. We know what its variance is. So what we get is that the probability Xn bar, its expectation is mu, so we subtract that off, put some absolute value bars. Square root of its variance is sigma over root n, because its variance is sigma squared over n. Probability that's bigger than or equal to epsilon is less than or equal to the variance, sigma squared over n, over epsilon squared. So if we apply Chebyshev's, we get this statement. And notice that as n goes to infinity, sigma squared over n epsilon squared goes to 0. Sigma squared is fixed, epsilon is some choice, and it just decreases like 1 over n. So why is this useful? Because we can use it to show that Xn bar converges in probability to mu. Okay, right? This was our whole statement we wanted to show. So we can show that Xn bar converges in probability to mu given our derivations, right? If we go back to what we're actually doing, right? So we go back up, we're talking about the weak law of large numbers. And the weak law of large numbers is that Xn bar converges in probability to mu. And so Chebyshev's, you know what? This was not Chebyshev's. What was our show? Let's actually go back and look at it. Chebyshev's was, we didn't have the square root of variance. It was just if x, it was just this, right? And so we actually don't have this sigma root variance in the bottom. We just get this, right? Let's rewrite that. And so go back and look at your notes. This is the correct form for it. Just be careful to use the right form. And so if we apply it to Xn bar, this is what we get. And we wanted to ultimately show that Xn bar converges in probability to mu. And if we can show that, because what we need to show is that to show that Xn bar converges in probability to mu, we need to show that for all positive epsilon, probability that Xn bar minus mu greater than or equal to epsilon converges in n as n gets large to 0. And what we've done is we've showed through this statement that the probability Xn bar minus mu is bigger than epsilon is bounded above by something that converges to 0. So we can show this statement because what we showed above is that Xn bar minus mu bigger than or equal to epsilon is less than or equal to sigma squared over n epsilon squared, and that thing goes to 0 as n gets large, and so the probability must go to 0. And that shows what we want to show, which is that Xn bar converges in probability to mu. So that's actually the whole proof of at least a simpler case of the weak law of large numbers. So you can actually go forward and prove it now. There's also so-called strong law of large numbers. And we're going to write that down, and we're not going to prove it. Strong law of large numbers. often abbreviated SLLN. And this says pretty much what you would think. It says that if I have x sub I, and these x sub I are independent and identically distributed, with expected value of each of them being mu, and variance of each of them being some finite sigma squared, the strong law says not that Xn bar converges almost surely to mu. So the weak law says it converges in probability. The strong law says it converges almost surely. But we need a little bit stronger assumptions. We need them to be IID and have a finite variance. If you look back at our weak law, we proved we didn't quite prove the full weak law. Nope. But we proved a version of it. But if you look back at a weak law of large numbers, you just need them actually, you don't need them to be independent, they need to be uncorrelated. And they don't have to have the same distribution. They have to be uncorrelated with the same mean and a finite variance. So it's the assumptions of this theorem are a little weaker. And because of the weaker assumptions, we can prove a weaker convergence convergence mode, namely convergence and probability. If you want to prove convergence almost surely, then the strong law of large numbers can be proved, but you have to assume they're IID. So a little bit more of assumptions needed there. Okay. So that's two ways of talking about how our mean, Xn bar, is kind of approximately going to give us an estimate of the sample mean. Xn bar is approximately going to give us an estimate of the population mean, mu. So you need the weak law says that, yeah, in probability under certain conditions it converges to mu. The strong law, under some stronger conditions it converges almost surely to mu, so even stronger statement. And the last way, corresponding to our last mode of convergence, is convergence and distribution, and this is known as the central limit theorem. So, theorem called the central limit theorem. And the central limit theorem is a centrally important theorem. It's probably one of the most important theorems in all of mathematics. It's a very powerful theorem. And it basically tells you in what way, in what kind of distributional way Xn bar converges towards the mean. So you've seen it in, say, an intro stats course. Now we're going to write it out the correct way. So the correct way to write the central limit theorem is that if we have some x sub i's and they are IID and they have an expectation mu and a variance, which is some finite sigma squared, then if we look at the following quantity, square root of n times Xn bar minus mu over sigma, that quantity converges in distribution to a normal 0, 1 random variable. So that looks much stranger than what you're normally taught in an introductory stat course. In intro stats, they'll typically say something like Xn bar is approximately normal mu sigma squared over n for large values of n. They're kind of vague about it. That's not a very mathematically precise statement. What does it mean for something to be approximately distributed as? What they really mean is what we wrote, which is that if I look at root n xn bar minus mu over sigma, that thing should be approximately normal. That thing should converge in distribution to a normal 0, 1. Notice that if xn bar were distributed normal sigma square over n, then if we looked at xn bar minus mu over sigma times root n, that indeed would be a normal 0, 1. So that's where the form comes from. You could also think of this thing as, you could move the root n, you could say sigma over root n, which some people like. But statisticians tend to leave the root n out front like that. So the form of our CLT here makes some sense. If x bar were really normal 0, 1, that thing would have an exact, or sorry, if x bar were normal mu sigma squared over n, that thing would have a root n x bar minus mu over sigma would have a normal 0, 1 distribution. In general, x bar isn't normal, but asymptotically, this quantity still is normal 0, 1. So that's the power of the CLT. It's giving us, it's telling us about the limit of the distributional behavior of x bar. It says that if we normalize x bar properly, it becomes normal 0, 1. And in practicality, people work with this statement. That's kind of how one thinks about it. So the practical way you learn intrastats is fine, but precisely the statement we wrote is mathematically how you actually show that. And when we're going to go and prove it, we'll actually need to rigorously prove it with convergence and distribution. Okay. You can look at some examples, just some real quick examples of the CLT. For the CLT, for example, if I have some x sub I, they're IID, let's say Bernoulli, with some unknown p, remember that the expected value of x sub I is p, and the variance of these x sub I is p by 1 minus p. And so the CLT in this case says that if I look at root n xn bar, so the mean of the first n of these, subtract off mu, which is the expected value, which is p in this case, and divide through by the square root of the variance, which is root p by 1 minus p, says that this thing converges in distribution to a normal 0, 1. So for Bernoulli, x bar minus p over root p times 1 minus p, all that times root n, that will converge in distribution to a normal 0, 1. And so what you learn in intro stats is if we could fudge it, so if we cheat and we say something like, okay, root n xn bar minus p over root p times 1 minus p is like approximately a normal 0, 1, then what we get is that x bar is kind of approximately, cheating in our notation here, but it would kind of approximately be a normal with a mean p, and so you just algebraically solve, and a variance of p times 1 minus p over n. And so in intrastats, when you look at, this should start to look familiar, if I want to estimate a proportion I look at p hat, which is really just Xn bar. It's the mean of my responses, my 0 and 1s, and you say that thing is approximately normal p 1 minus p over n, and maybe you even have a confidence interval, and my confidence interval is p hat plus or minus, say maybe 2 standard deviations, and the standard deviation is root p times 1 minus p over n. So that's where all that comes from in interest stats. Straight up central limit theorem. So let's, as a kind of final exercise, let's do a little proof of the central limit theorem. And this proof of the central limit theorem is going to reinforce my claim that the moment-generated functions, while a little bit strange at first, are really important, because we're going to prove the CLT using MGFs. So before we prove the CLT, we have to remember something from Calc 2 called Taylor's theorem. And Taylor's theorem says that if I have some function, some real valued function, r to r, that is k times differentiable, then the kth order Taylor approximation, Taylor polynomial, about some number a is, we define this thing, let's say t for Taylor, k for the kth order, at x. If we expand it around a, it's the sum, where r goes 0 to k, of the rth derivative of g, evaluated at a, divided by r factorial over x minus a to the r. So this should be familiar from Calc 2 with Taylor series. We call r our function minus tk of x, the remainder, and this thing goes to 0 as x goes to a, and it goes to 0 quickly, and you can precisely define that. So if I have, basically what happens is, if I have some function g, I can approximate g using my kth order Taylor polynomial. I pick some center a, I form this kth order polynomial, which uses derivatives of g, and otherwise it's a polynomial. If I do this, then the remainder, the difference between my truth and my kth order approximation, my kth order polynomial, goes to 0. So for x near a, Taylor's theorem says that g of x is approximately tk of x. That's what it's saying, is that I can approximate g as this Taylor polynomial as long as my x is somewhere near a. And the higher my value of k is, the better the approximation. Okay. So let's look at how to apply this. So that's just to recall from Calc 2, that fact. So let's look at how this Taylor series can be used to prove the central limit theorem. So let's go back first and let's look at what our definition or our statement of the central limit theorem was, right? So the central limit theorem said that if we have x sub I, which are IID, with each of them having a mean mu, and each of them having a variance, which is some sigma squared, that's finite, then we define Xn bar as 1 over n, sum goes 1 to n of the x sub I. If we properly normalize x bar, so we look at root n Xn bar minus mu over sigma, we can show that that converges in distribution to a normal 0, 1. Okay? So this is the statement of the CLT. So let's look at a proof of it. So first, let's call this whole thing on the left side here y. So let's y be root n Xn bar minus mu over sigma. And we're going to show that if we let y sub I basically be the z-scored version of x sub I, so we take x sub I, we subtract off the mean, divide through by sigma, then this y sub I, these y sub i's are related to the whole thing y, as y is the sum of 1 over root n times the sum of these y sub i's. And you can convince yourself of that because 1 over root n sum I goes 1 to n of xi minus mu over sigma. So that's what the sum of the y sub i's are. And if I multiply, well, we can expand it out, right? So I'll pull out my 1 over sigma. I'm left over with a 1 over root n. Sum I goes 1 to n times x sub I, and then I get n mu's out of my sum, and I have to divide through by root n. So this is what I get. Whoops. Nope, that's right. And I can write 1 over root n as n over root n. This is n over root n, 1 to n, x of I. And I can write this as root n. I'm sorry. 1 over root n is root n over n. N over root n is root n. So root n mu. And then I'm going to factor out that square root of n. And I'll be left with 1 over n times the sum of my x sub i's minus mu, and the whole thing, we can put my sigma back in there. And so that is, as claimed, is y minus mu over sigma times root n. So this is my relation. Notice that each of these y sub i's, if we look at the expected value of y sub I, it will be 0, and the variance of these y sub i's is 1. We've chosen our normalization by subtracting off the mean, dividing through by standard deviation. We ensure that these two facts are true. So we have that the overall thing we want to find the distributional limit of is 1 over root n times the sum of these standardized in some way y sub i's. And we have a theorem, so let's bring this all down. Let's just rewrite this, that y is 1 over root n times the sum, I goes 1 to n of these y sub I. And notice that the y sub I are independent because the x sub I, upon which they are based, are independent. And so if we look at the moment generating function for y, and y of t, we have a theorem that says y is 1 over root n times the sum of the y sub I. Because these are independent, we have a theorem that, this thing, evaluated at t, is the moment generating function of any of them individually, let's just call it m, at t over root n to the nth power. And that comes from a fact about moment generating functions. If you go back to our lecture on independence, you can show that to be true. That the sum, the MGF of the sum of independent things, of independent IID things, is just these independent, the moment generating function of any of them to the nth power. And if we multiply by a constant, way back to just after test 1, we showed that you could just bring the constant into moment generating functions. And so we can write that in the side, right? M of the sum of the x sub I of t is m of t to the n, if these x sub I are independent, and m of a times some x at t is m at at. Right, so these are our two facts. If we go back to our lectures on MGFs. Okay, so we're getting somewhere. The MGF of y is MGF of any of these y sub I at t over root n to the nth power. And what we're going to do now, so let's box this fact, is let's do a Taylor expansion of m. So this m here is the MGF of any of our y sub I. They're all the same MGF because they're all the same distribution. So we're going to expand m. We're going to do a Taylor expansion around 0. So and above in our Taylor theorem, that is at a is equal to 0. So our Taylor expansion, m of t, is, we can write, if we have let's do a second order. So let's do second order Taylor expansion. So expand it as 2 terms, or as 3 terms, but R goes 0 to 2, right? It's a second order expansion. And remember, our Taylor expansion is the rth derivative. We're expanding around 0, so we plug in 0, divided by r factorial times our variable, in this case t minus 0, okay, to the rth power. So in our case, so we know that m of t is this Taylor expansion, is this Taylor polynomial, secondary Taylor polynomial, plus some remainder that depends on t, but r of t will go to 0 as t goes to 0. So if we can simplify this a little bit, the 0th derivative is just going to be defined as 1, right? And so it's 1 times t to the 0 over 0 factorial. That's going to be the convention of the 0th derivative, plus the first derivative, m1, evaluated at 0, times t minus 0 to the first power over 1 factorial, plus our second term, our third term, our second derivative at 0, t squared over 2 factorial, plus our remainder that depends on t. So simplifying even more, the first term just turns into a 1. The second one is expected value. So the first derivative of the moment generating function at 0 is just the expected value of any of these y sub I, right, times t. The second moment and the second derivative evaluated at 0 is the second moment multiplied by t squared divided by 2, and then we have r of t. And we know from above, we noted that this thing is 0, and the second moment is, because the mean is 0, the second moment is the same as the variance, and that will be 1. And so overall, we get 1 plus t. I'm sorry, that disappears, right? We get 1 plus t squared divided by 2, plus some remainder r of t. So what we showed here, so this is, of course, this is our MGF for any of these y sub I individually. So you could say it's m y sub I if you want. And so let's recap the facts that we've developed so far. So what are our facts? 1, m of t, or m of any of these individual little y sub I, is 1 plus t squared over 2 plus r of t. And the second fact is that the moment generated function of y, so recall that y is the thing we're actually interested in, x bar minus mu over sigma, this thing, is m of t over root n to the nth power, which, plugging in fact 1, gives us that it is 1 plus oh, wait. Yeah, 1 plus t squared over 2n plus r of t, and all of it to the nth power. And our argument here is that if I look at the limit as n goes to infinity of m y of t, notice that y depends on n, so don't explicitly say it, but it does. That is the limit as n goes to infinity of 1 plus t squared over 2n plus, oops, this should not be r of t, right? This should be r of t over root n, right? Because we plugged in t over root n, right? So this should be r of, gotta be careful here, t over root n. And all of this to the nth power. And this, r of t over root n, will go to 0 as n goes to infinity, because t over root n goes to 0. And we know r of t goes to 0 as its argument goes to 0. And the rest of it looks a lot like e to the t squared over 2, right? How can we see that? The rest of it is basically the limit as n goes to infinity, 1 plus t squared over 2 over n to the nth power, and that is e to the t squared over 2. So the limit, just to recap, the limit of the MGF of this quantity, in which you're interested, is e to the t squared over 2, and that is the MGF of a normal 0, 1 random variable. And so since the MGF, so it's slightly cheating here, we're going to use the theorem we haven't quite proven, but since the MGF of this thing, which is what we've just shown, Xn bar minus mu over sigma, this thing converges to the MGF of a normal 0, 1, then we're going to say the CDFs also converge. We put a star here. We didn't show that, but it's true. The MGFs converge, the CDFs converge. And so if the CDF of Xn, of root n Xn bar minus mu over sigma converges to the CDF of a standard normal, this converges to, in distribution, to a standard normal. And that's the CLT, at least that's a simple proof of a version of the central limit theorem. And basically it used definition of the moment generating function, Taylor's theorem, definition of E, and definition of convergence and distribution. But that's a nice, I think, nice way to kind of end out the course.